All right, coordinate vectors. Let's find exercise 3.3.5. Find a coordinate vector. We'll start with a relatively easy one of a vector v in R3, the vector 3, 13, negative 1, relative to the ordered basis of R3 as given here. We're trusting the book that they've given us something that actually is a basis, a linearly independent spanning set. So first, recall what a coordinate vector is. This is definition 3.8 in the notes in the book. Recall that a coordinate vector v sub b of a vector v with respect to, let me abbreviate a little bit because of my space limitations, vector v with respect to ordered basis b, a coordinate vector v sub b of a vector v with respect to an ordered basis b is the coefficients of the elements of the ordered basis that produce vector v. So we need to find coefficients. We need how many coefficients? 3 basis vectors. So we need R1, R2, R3, 3 coefficients, such that when we take a linear combination with these coefficients of the basis vectors, we get vector v out. So we need R1 times the first basis vector, 1, 3, negative 2, plus R2 times the second basis vector, 4, 1, 3, R3 times the third basis vector, negative 1, 2, 0, and we need to get out vector v, 3, 13, negative 1. Okay, 3 unknowns. I wish I had 3 equations, eh? So let's do the arithmetic, do the linear combination stuff on the left. That'll produce 3 components on the left, 3 components on the right, and there comes the 3 equations and 3 unknowns. So combining the vectors, we get R1 plus 4R2 minus R3. First component, second component, 3R1 plus R2 plus 2R3. Third component, negative 2. R1 plus 3 R2 and 0 R3s. And we still need that to equal 3, 13, negative 1. Take the linear combination. Here comes 3 equations and 3 unknowns. We need solution to this system of equations.
Dinner's about ready.
R1
It is ready.
plus 4R2 minus R3 equals 3. 3R1 plus R2 plus 2R3 equals 13. Negative 2R1 plus 3R2 equals negative 1. So consider, so we'll change it into an augmented matrix. 1, 3, negative 2, R1 coefficients, 4, 1, 3, R2 coefficients, negative 1, 2, 0, augmented with 3, 13, negative 1. So we find R1, R2, R3. We found the coordinate vector of vector v with respect to this ordered basis. Now Wolfram alpha tells me if we row reduce this, then we get the following. Better have a unique solution or else we don't have a basis. And it produces this output. So 2, 1, 3 are the values of R1. R1 is 2, R2 is 1, and R3 is 3. So the coordinate vector of vector v with respect to basis b, ordered basis b, is just the vector R1, R2, R3. In this case, 2, 1, 3. There's the coordinate vector. Finding coordinate vectors is nothing more than finding coefficients in a particular linear combination. It's a linear combination based on ordered bases.